Hello, everyone. Hope everyone's doing well. I'll get started in a couple of minutes with today's session. We're doing periodicity today. So we'll start with classification. We'll talk about how the periodic table works, and then we'll talk about trends along the periodic table. Yeah. Cool. Let's get into it. So, classification. So how does the periodic table work, basically? So we'll talk about the meaning of these terms again. So a period is a horizontal row in the periodic table. So elements in the same period will have the same number of electron shells, whereas a group is a vertical column in a periodic table, and elements in the same group of the periodic table will have the same number of outer electrons and therefore similar chemical properties. The proton number determines the position of an element in the periodic table. So elements are arranged according to increasing proton number. And the proton number is just the number of protons, which is also the atomic number. The mass number is the number of protons plus the number of neutrons. The number of neutrons can therefore be calculated by working out the mass number minus the atomic number. And the number of protons will equal to the number of electrons in an atom. An element's chemical properties are defined by its electronic structure. The position of an element in the periodic table tells you a lot about its electron structure and hence a lot about its chemical properties. So you can see that they're arranged according to electron structure. So you can see all the elements with the s orbital are at one side. All the elements with the d orbital are in the middle. P are the non-metal side. So if you think about it, the s block elements only have 1 or 2 electrons in their outer shell, which means that they can lose those electrons very easily, and therefore s block elements are considered very reactive. They can also conduct electricity easily via their delocalized electrons. D block elements have an outer shell configuration between S2p6 3d1 and S2p6 3d10. And again, because of this variable structure, they can lose different numbers of electrons, which means they can have variable oxidation states, which is a feature of metals. Your p block elements have either 5, 6, or 7 electrons in their outer shell, so they're going to gain electrons to form negative ions, and the elements can also share electrons to form covalent bonds. And then your noble gases, group 8, have a complete outermost shell of electrons. These elements are inert because they do not transfer electrons. They're noble or inert gases. Okay, trends along period 3. So, if you go along period 3, what you're going to have to think about is what's actually happening. Well, the number of electron shells is going to stay the same, right? you still will have 2 electron shells. But your nucleus, which is in your center, your nucleus is going to become stronger, which means, because it's going to get more protons, which means the force that it's exerting, the attractive force that it's exerting on these electrons is going to be greater. So it's going to be stronger attraction between the nucleus and the electrons, which means that the force pulling the electrons inwards is going to therefore be greater, because electrons are pulled inwards stronger towards the nucleus. That means that the atomic radius is going to go down, because if you imagine it, it's sort of pulling much stronger, which means it's holding on, it's tighter, which means it comes in closer. It's the best way to think about it. So atomic radius decreases as you move across a period, because the proton number increases, which means there's a stronger attraction between the nucleus and the electrons. And then electrons are pulled inwards towards the nucleus and the radius is contracted inwards. So as you can see, the atomic radii has a general downward trend. The melting point across a period will change, but it will change based on the structure and bonding types that are present. So let's start from sodium to aluminium. Sodium to aluminium are metals, so they're going to have metallic bonding. But you can imagine that the metallic bonding, which we have talked about in our bonding and structure lesson earlier, so if you are kind of struggling a little bit to understand metallic bonding, go back to that lesson first. Very important to get the basics down before you move on to more advanced content. But if you're going across, the number of delocalized electrons is becoming higher, because the ions are, it goes from Na plus to Mg2 plus to Al3 plus, which means that each ion or each atom is losing more electrons as you go along. So the number of electrons is going to increase, which means that the metallic bonded attraction between the positive ions and their sea of delocalized electrons is going to be greater, which means that the strength of attraction is going to be greater, which means that the ions or the melting point is also going to increase, because the number of delocalized electrons present will be increased. There'll be a smaller electroatomic radius, which means that the strength and the force of attraction is going to be stronger, which means that the melting point is going to be higher, because there's a greater electrostatic attraction between the positive ions and the delocalized electrons. Okay, what about silicon? High or low melting points? So silicon has a very high melting point because it's a macromolecule. It exists as S8. So lots and lots of molecules of silicon covalently bonded together. Covalent bonds are quite strong, which means that there are lots and lots of strong covalent bonds, which require a large amount of energy to overcome, which means silicon has a high melting point. Okay, melting point from phosphorus, sulfur to chlorine. Well, interestingly enough, the melting point from phosphorus, sulfur to chlorine kind of goes a bit like this. It goes up and then it goes slightly down, but the overall trend between phosphorus, sulfur, and chlorine. Why is this? Because phosphorus, sulfur, and chlorine are simple molecular substances, which consists of van der Waals forces. Van der Waals forces are weak intermolecular forces that need a small amount of energy to break. They're simple molecular substances which have a low melting point. So if we think about what's happening between P4, SA, and Cl2, is the number of electrons goes up, which means that the induced dipole-dipole interactions become stronger, which means that the melting point becomes higher. The shape of the molecule and distance therefore affects the strength of the induced dipole-dipole forces. So a larger molecule contains more electrons, has larger electron clouds, which means that the greater the number of electron clouds, the stronger the induced dipole-dipole forces, because there are more electrons in those electron clouds, which means as they're rotating in their shells, these induced dipole-dipole forces are going to become stronger. And so therefore, more energy is required to break these stronger induced dipole-dipole forces. And because sulfur contains the most number of electrons, sulfur contains the strongest van der Waals forces, which means that sulfur will have the highest melting point. Makes sense, right? Logical. Okay, argon, high or low melting point? Everyone have a thought internally? Argon, high or low? Argon is going to have a low melting point. Why? Because argon is a noble gas, which means it exists as a monoatomic element and has very weak van der Waals forces. Due to these very weak van der Waals forces, there's a small amount of energy needed to break them, hence argon has a low melting point. Okay, last quick discussion about trends. Ionization energy. Does that increase or decrease across a period? Think about what we already know. We know that the electron, the atomic radius, goes down because the strength between the nucleus and the outer electron goes up, which means that there's more force holding those outer electrons in. So then what do we think? Do we think the ionization energy is going to go up or down? Going to increase, right? Because across the period, there's going to be more energy or more force holding that outer electron in place, which means that it's going to be more difficult to remove that outer electron. Sort of makes sense. Yeah. So the proton number increases means a stronger attraction between the nucleus and outermost electrons, which means that more energy is required to remove the outermost electron. Makes sense. Quite logical. Okay. Next up is so we're talking a little bit more depth about these ionization energies that I've just brought up, because I brought them up very roughly at the end of that last bit. But what is an ionization energy? Well, so when the s block elements form a positive ion, these ions will have the same electron structure as that of an inert gas, because they've lost an electron, which means that they basically will have the same electron structure as the atom, as the element before them. When p block elements form a negative ion, they also have the same electron configuration as that of an inert gas, because remember, they gain the number of electrons needed to get themselves a full outer shell. Because remember, that's the aim of every element. If the one rule of chemistry that once you understand this rule, everything sort of starts making sense. And the rule is every element or every atom is trying to get a full outer shell. That's its goal. That's its own goal. So in any way necessary, it is going to try and get a full outer electron shell. Okay, so ionization. Ionization is in the name. Ionization is the process by which an electron is removed from an atom or a molecule. And ionization basically is the process by which an atom becomes a plus ion, a positive ion. And this is an endothermic reaction because energy is required. You need to add energy to break the force of attraction between the electron and the central positive nucleus. There's a force of attraction. you need to add an energy to remove that electron. So this is a really important definition. So I'm going to pause a bit here. First ionization energy is the energy required to remove one electron from each atom of an element in 1 mole of gaseous atoms to form 1 mole of gaseous ions with a +1 charge. This is really important to know. I'm going to pause for a second here to let you write this down. To the person who's asked, do we get access to the PowerPoint? No, but all the recordings are on YouTube. So if you want to go through it slightly slower, the better bet is to just go back over the recording and pause when you need to. But I will pause at bits that I think are very important for you to get down. The second ionization energy, therefore, I'm not going to pause here because it's very logical, self-explanatory here a little bit, is the energy needed to remove one electron from each ion of an element in 1 mole of gaseous +1 ions to form 1 mole of gaseous +2 ions. Makes sense? And let's take a remarkable guess at what the third ionization energy definition would be exactly the same. So a successive ionization energy is the energy needed each time you remove an electron, and a graph for a particular element of successive ionization energies will be typically drawn. Remember, this all happened in gaseous states, and so you need to remember that you're using gaseous states to do this. Okay, so we remember that a period is a horizontal row in which all the elements have the same number of electron shells, and a group is a vertical column in which all of the elements have the same number of outermost electrons. The shielding effect is basically the increasing number of electron shells will prevent the force of attraction going to the electron shells behind them, which basically means that there's a reduction in pull of the nucleus to the electrons, the greater the number of shells there are. And the effective nuclear charge is a measure of how positive the nucleus is. So it's the net positive charge experienced by the outermost electron, taken into account 2 factors: the repulsion from shielding electrons, but also the attraction from the positive nucleus. And the size of the ionization energy is therefore determined by your relative effective nuclear charge, because the more there's shielding, the lower the ionization energy will be, and the more the nuclear charge, the higher the ionization energy will be. So the 3 factors that affect ionization energy is the atomic radius, the nuclear charge, and the shielding effect. So higher the atomic radius means that there's a greater shielding effect, which means that the attraction from the nucleus to the outer electron is going to be less, which means that the ionization energy will be lower because it's much easier to remove an electron. I will stop here because this is something important to take down. So I'll stop for a second or two here. Doesn't a higher nuclear charge means there'll be more shielding? No, a higher nuclear charge means that a higher nuclear charge doesn't really affect the shielding effect. The shielding is just to do with the number of shells. Shells do shielding. That's it. There's nothing else that does shielding. Okay, nuclear charge. The higher the nuclear charge, the higher the ionization energy, because there is a greater force of attraction. The nucleus has a greater pull capacity, which means it's pulling on these outer electrons the force is much greater, which means that it's going to be harder to remove the electron, and therefore it's going to be it's just going to be more effective. It's going to have a higher ionization energy because it's going to be harder to remove that electron. And then the last option is inner shells. So the more inner shells, the lower the ionization energy, because the more shells, there's more electrons to repel the outer electron, which is pushing back against this increase in nuclear charge. There's a greater shielding effect, which means that it's harder to remove that outer electron, which means it's easier to remove the outer electron, because there is a greater shielding effect present on those electrons. So which one of these will have a higher ionization energy? It's actually going to be the one with the one with less shells and a lower radius than the one with the lower nuclear charge. And the reason is because the nuclear charge, the shielding effect is a much stronger effect. It outweighs the increase in nuclear charge. It is much more potent at reducing the ionization energy than having an increased nuclear charge. Successive ionization energies is really important because when you're looking at tables with successive ionization energies, whenever there's a big jump in ionization energy, you need to remember that that's the point where there is a new shell that's being broken into. So whenever there is a sudden rise in ionization energy, it means that a new shell has been broken into. You can see at the first ionization energy, there's a jump. But whenever there's a big jump, it means that you've removed the electrons in a particular shell. And successive ionization energies increase within each cell, within each shell. So every time an electron is removed, even if you haven't broken into the new inner shell, the ionization energy will still increase, because if you think about it, at the beginning, the number of electrons equals the number of protons. But the minute you remove one electron, the number of protons now is already greater than the number of electrons, which means it's already going to have a net stronger effect on the remaining electrons. And every time you keep taking away more electrons, the effect of your protons, even though the proton number is not increasing, the effect of the protons is going to be greater. It's just going to keep increasing and increasing. So your second ionization energy is always bigger than your first ionization energy. The big things that you're looking for is when there's big jumps, which indicate that a new shell has been broken into. So as you can see here, can someone identify which group this ionization energy, which group this structure is in? From this group one, Molly, you're saying why would people say group one? It is group one. It's group one because there's a greater jump at the second ionization energy. So at this point, you are at AR. Yeah. Then at this point, you have the same ionization energy as fluorine, and it would be group one. And you can see it at the top because it's actually been written here, graph showing successive ionization energies of sodium. So the group of the periodic table it belongs to can be found out by counting the number of electrons removed before the first sudden rise in ionization energy. So this one has one electron removed, so it's group one. And the first ionization energy is the energy needed to remove one electron from each atom of an element in 1 mole of gaseous atoms, forming 1 mole of gaseous plus 1 ions. You just need to remember that. And we've talked about this trend. So down a group, the ionization energy decreases because remember, the atomic radius is going to increase. There's going to be an increase in the number of electron shells, which means that there's going to be even though there is the increase in nuclear charge, this is outweighed by the increase in atomic radius and the increase in shielding, which means that there's a weaker attraction between the nucleus and the outer electron, which means that it's easier to remove the electron from the outer shell. So as you can see, atomic radius increases as you go down a group in the periodic table because an extra shell is added each time. This decreases ionization energy. There's an increase in the number of shielding electrons. This decreases ionization energy. And there is an increase in nuclear charge. This increases ionization energy, but is outweighed by atomic radius and shielding. I'm going to let you write this down because this is quite important. And this is how you'd structure it in an exam if you were asked to do this for an examination. And then across a period, remember you have the same shielding effect. You actually have a decrease in atomic radius due to that increase in a nuclear charge, but the same number of shells, which means that there's an increase in nuclear charge, which means that the electrostatic force of attraction between the central nucleus and the outer electron goes up, which means that the ionization energy goes up. Overall, I'll give you a second to write this down. And you can see there are a couple of dips, and we'll discuss these in a little bit about the dips. So the first drop is the ionization energy is between groups 2 and 3. And this one is quite simple to understand, because if you imagine that between group 2 and 3, what's happening is you're going from an S, a full stable S subshell, into an unopposed electron in a P subshell. That unopposed electron in a P subshell is not being held in place by anything, which means that the first ionization energy is going to drop. So that S2 is full, it's stable, but that P1 is an unopposed electron in a P subshell, which basically means that it's going to drop because it's much easier to remove from a single electron from a P subshell. The second drop is between group 5 and group 6, so nitrogen and oxygen. You go from S3, SP4. And the reason is because if you imagine the P subshell is split into 3 orbitals, nitrogen has 3 electrons in the P orbital, but oxygen has 4, which means it has 1 upspin and 1 downspin electron in an orbital. This then means that this electron, this downspin electron, is now undergoing, it's feeling the effects of the repulsive forces from the upspin electron in that orbital, which basically means, so it's not at a position of stability, it's not at P6 yet, or P5 where it's relatively stable, it's still unstable, and it's feeling the repulsion from being now an opposed electron in a orbital. This means that it is going to be easier to remove that electron because of the repulsion that it is experiencing. That's kind of it for ionization energies. Let's talk about some of the group 2 alkaline earth metals. In this meantime, I'm actually going to stop because this is most of periodicity kind of done. So I'm stopping to answer any questions that anyone might have. I'll stop for maybe about 5 minutes, let people have a break, and answer any questions that might come up about periodicity. We're going a little bit ahead, so. Any questions? In the meantime, I'll put a link in the chat. If people can fill out a review, it'd be very helpful. It would help me particularly, help me see where my what's positive and what's negative about this. If you can fill out this review. So are van der Waals forces the same as intermolecular forces? No. Intermolecular forces is an umbrella term for a variety of different forces. So you can have permanent dipole-dipole interactions, hydrogen bonding, but you can also have induced dipole-dipole van der Waals forces. But intermolecular forces is a massive umbrella term of different types of intermolecular force. Van der Waals forces are specifically the induced dipole-dipole interactions. Where can we get access to this PowerPoint? I can't provide you access to the PowerPoint. You'll need to watch the recording again on YouTube if you want access to the slides or anything that was particularly said. Okay, what would a graph look like for ionization energy for group 3? It would literally just be downwards. So it'd kind of just be a downward line if we imagine it. It'd probably be graduating downwards. So probably won't be a straight down, but it would just be a decline. But you wouldn't need to be able to identify it. They wouldn't give you that graph before. I don't understand why first ionization energy is higher in the p orbital. Shouldn't it be higher for 2s2 because of the repulsion helping kick one of the at one of the electrons? No, because 2s2 is stable. So 2s2 is kind of, it's a full orbital. A full orbital, remember what I said the first rule of chemistry was, things like being full. Orbitals like being full, shells like being full, things like to be full in chemistry. So when the orbital is full, it's at a position of stability. That is kind of where it wants to be, where it's meant to be. So the p is an unopposed electron. It's a single electron that doesn't really have the stability that the 2s2 electrons would have. And Km is, I can't see your name in the chat, but that I've just explained it. So it is because they're at 2s2, at group 2, 2s2, they're stable, paired electrons, stable orbital, whereas group 3 is an unpaired p electron, which means that it's unstable, which means that it's easier to get rid of. Did I say I would send the PowerPoints? No, I can't send the PowerPoints to you guys. So my best advice would be to watch over the recordings if there's something that you've missed, taking down in the notes. What revision techniques would I suggest for chemistry? Best revision techniques, probably doing practice questions, as many as you can. Just keep doing practice questions. That would work for me. I used to do this thing where I would basically get a piece of paper and write everything I knew about a topic and then check against my notes to see whether that was correct. I find that quite time consuming. And I think in hindsight, I wouldn't have done that. I probably would have gone and done flashcards or something. But the best thing that you could do for yourself is do active recall. It's making your brain actually think. So reading, highlighting, mind maps, if you're using your textbook to make the mind maps, probably aren't particularly helpful. Your brain needs to get into the habit of actively bringing out that knowledge like it would have to do in an exam setting. And that's the best advice I can give you for chemistry. Right. Give you group 2 elements. So trends in group 2. So group 2 elements form ions with a +2 charge when they react. Their outer shell contains 2 electrons, and they will lose 2 electrons to get a full outer shell of electrons. Kind of makes sense. We've been talking about this all day. Group 2, beryllium all the way to radium, beryllium, magnesium, calcium, kind of etc. as we go down. Group 2 trends. So what happens to atomic radius down group 2? We should know this already. People put it in the chat. Let's see. Yeah, everyone's getting it. It's going to increase. Yeah, because remember, more and more electron shells are being added, which means that the atomic radius is going to go up. Kind of makes sense. And this is kind of what the graph looks like. What about melting point? So let's think about that. Melting point decreases. Why? Because the radius of the metal ions is going to increase, which means that the number, it's still only 2 delocalized electrons, but the radius increases, which means that the attraction between the nucleus and those delocalized electrons is going to go down, which means that less energy is required to break these metallic bonds. And therefore, it makes sense that the melting point is going to go down. You can see the general decrease. First, ionization energy. Can we think about what's going to happen down group 2? We should already know this. This should be revision for most people. Yeah. Anyone else? Kind of want to have a guess? No, yeah, you guys are on the right lines. It is going to decrease. Again, as more electron shells are being added and the atomic radius increases, there is less attraction between the nucleus and the outermost electrons, which means it's easier to lose that outer electron because less energy is required to remove it. Kind of makes all the sense. What about reactivity? Is this slightly more difficult? Well, I mean, this should be something that we do know, but might be a little bit more challenging. What happens to reactivity down group 2? Let's see if we can put it in the chat. Yeah, Molly, completely correct. It does increase. Why does it increase? Well, reactivity doesn't decrease, it increases. Because remember, you need less energy to remove those electrons. So it's easier to move the electron, which means that it's more reactive, right? If it's easier to do something, then it's more likely it's going to do it, which means that it's going to be more reactive. That's kind of the logic that I use around it. The other kind of logic that I think about it is if you imagine the reactions, they become more vigorous. They appear more, flaming. They appear more explosive. Why is that? Well, the way I think about it is a reaction has two kind of things. It's got to do what it's got to do, which is remove the electrons. And then any residual energy is being used up to do the nice explosions that we like to see. If it takes less energy to remove those electrons, it's got more energy to go and do the explosions. That's another way of thinking about it. There are two ways of thinking about why, although the ionization energy will decrease, the reactivity will increase. There are two kind of ways to think about that. Okay, reactions of group 2 elements. So this will kind of be a quick recap because again, it should be something that we do know, but I will stop at different points here. So group 2 elements react with oxygen to form a metal oxide. So 2M plus O2 gives you 2MO2. That's kind of your generic formula for that. It's an important one to know. You want to write this down? Give you a second. And again, different metals burn with different colored flames, which can be used as a test for the presence of 2+ ions. So the ones that you should probably be aware of is beryllium, magnesium is white, calcium is brick red, strontium is scarlet, and barium is apple green. These are some of the ones that you should be aware of. And again, when you're going back over the recording, you might want to stop and write these down. Group 2 elements also react readily with water to form a metal hydroxide and hydrogen. So M plus 2H2O gives you metal hydroxide plus hydrogen. So calcium plus water gives you calcium hydroxide plus hydrogen. And again, this hydrogen will appear as effervescent and fizzing. And this fizzing we can then detect. So remember, reactivity just increases as you move down the group. Beryllium doesn't react at all. Magnesium reacts very slowly and barium reacts rapidly. You've probably seen this experiment in class done before. And again, it's a metal hydroxide. Metal hydroxide will dissociate hydroxide ions, which means it will form an alkaline solution. In the case of steam, group 2 elements react vigorously with steam to form a metal oxide. So not metal hydroxide, but they form a metal oxide and hydrogen. Really important to differentiate that. I'm going to give you a second to write this down here. Oxides then can react with water to form a metal hydroxide. So you can have two steps to this process as well. Group 2 elements react readily with acids to form salts and hydrogen. So group 2 element plus acid gives you a metal salt plus a hydrogen. I mean, you should probably already know these. So HCl, metal nitrate, NO3, SO4. And again, it depends on the anion that is present in the acid as to what the salt would be. Oxides react with acids to form metal salts and water as well. Hydroxides react with acids to form metal salt and water. Carbonates react with acids to form a metal salt, carbon dioxide, and hydrogen. Second. Okay, we're not going to talk about ion polarization because you don't really need to know about that. Thermal decomposition. So carbonates of group 2 elements decompose upon heating to give metal oxides and carbon dioxide. So that you do need to know. So carbonates, when they're heated up, will form metal oxides and carbon dioxide. And thermal stability of group 2 metal carbonates increases down the group, which means that the temperature required for the carbonate to decompose also therefore increases as you go down the group. Because the ionic radius increases, charge stays the same, charge density increases, which means that the ability to polarize also increases. Nitrates decompose upon heating to give metal oxides, nitrogen oxide, and oxygen. So that's really important to know. And again, this also increases down the group. The temperature needed to do this also increases down the group because there's a decrease in polarizing power. So if we think about the solubility, so solubility with singly charged negative ions increases, which means that if it's a metal hydroxide and it's soluble in water, that goes up as you go down the group. For example, magnesium hydroxide, which is used to cure acid reflux, is only sparingly soluble in water. But barium hydroxide, which is used as part of the barium meal, is very soluble in water. However, metal sulfates, when they're trying to be solubilized, that solubility decreases. I'm not too certain why. You just need to remember that with singly charged negative ions, the solubility increases. With doubly charged negative ions, the solubility decreases. I think it's quite complex chemistry, the reason behind it. So barium sulfate is insoluble in water and it forms a white precipitate. And remember, testing for sulfate ions is by adding, so you acidify and then you add a sulfate. So you add, first of all, you've got your ions, it forms barium sulfate, and then you do a substitution reaction with another kind of barium chloride, and then that displaces the sulfate ions, which can then be detected by the reaction. Cool. That's kind of it for periodicity. There's really not much else to talk about. Does anyone have any questions? Oh, I've been asked a question. Can we say SR has a red flame instead of scarlet, or would it be better to say scarlet? Technically, it's a scarlet flame, so it would be better to say scarlet, but red would probably be also accepted on your mark schemes. Metal oxide written as MO2 or MO. It's usually MO because the oxide ion is 2- and the metal ion is 2+. So it's just MO. If there are no other questions, the 2 as a subscript. No, it is still just MO, the metal oxide. If there are no other questions, I'll stay on. What topic is being covered next? Good question. So Friday biology lessons, as people know, hopefully. So please come along to those. Those tend to have a lot more people in them. I'm not too sure why, but yeah, so come along to the biology lessons as well. We've got one on Friday, which is going to be about exchange surfaces in animals. And then next week is spectroscopy, so AS spectra. So identifying organic chemistry structures. Cool. No worries. Thank you for coming. I will hopefully see you guys on